Okay, so I see that we have a good number of participants. We'll get started with the presentation. So hi everyone, and thank you for coming today. I'm Catherine, and I'm here with my teammate Mark, and we're here to present River. So River is a drop-in real-time service for web applications. It's cloud-native, easy to deploy, and ready to scale with your needs. We had lots of fun while building this project, and we hope to share a bit of that enthusiasm with you today. Now, I want to say a quick word about cloud native, as you might be wondering what that means. Cloud native means that River was designed and built with cloud services in mind. There are many buzzwords associated with cloud computing, but also a lot of very interesting ideas. We will explore some of these more in depth during the presentation. So who would use River and how would you use it? We target application developers. River is meant to be used alongside an existing application. It will allow you to easily publish events from your backend APIs, and these events will become available to web clients in real time. I'll start with a quick outline of this presentation so you know what you're getting into. So real-time is such a wide space that at first I want to clarify what real-time means in the context of web applications and which use cases we had in mind when designing River. I will then talk about why a separate real-time service might be a good idea, and Mark will walk you through an example of adding real-time functionality to an existing app. We will then look at some of the existing solutions before diving into how we built River and automated its deployment. Finally, we will say a word about how you can use it. So if we're talking about a real-time service, the first question we should address is, what is real-time? Real-time is a very wide space, and we want to narrow the focus a bit and clarify what we're about. Real-time is about a fast exchange of messages. A change will happen somewhere in our system, and other parts of the system should be notified as fast as possible. What as fast as possible means, though, varies quite a lot depending on the context. Are we talking about microseconds latency? Is a missed deadline considered a system failure? For us, the answer to these questions is no. Keep in mind that we're in the context of web apps. This is not about an airplane control system. Even within the realm of web apps, some systems are much more sensitive to delays than others. Gaming or financial stock trading could be examples here. In this case, a higher latency can have serious consequences. These are sometimes called firm real-time. Soft real-time is much more flexible. In that case, a higher latency will result in a worse user experience, not a system failure. Collaborative apps are a good example. You can think of a collaborative text editor, such as Google Docs, a discussion forum like Slack, or a shared calendar. The idea here is that the real-time application should update to the correct state without user intervention. These are the type of applications we had in mind while building River. Now, if you think of the HTTP request and response model, without user intervention would mean without the client sending a request. And that's not an option. What we need is an open channel of communication through which messages can be sent between the server and the client. With that idea in mind, there are a few options in terms of how the messages are exchanged. The first thing to notice is that the connection will always start with a normal HTTP request from the client. These are the blue arrows in this diagram. It would be a disaster from a security standpoint if servers could initiate a connection with the client. XHR polling, as it sounds like, means that the client will poll the server. This means it will make a request on a periodic interval to see if new data is available. With server-sent events, after the initial request and response, it's a one-way server-to-client streaming of text-based data. These are the green arrows. Finally, with WebSockets, we have a bidirectional message-oriented streaming of text and binary data between client and server, the red arrows to the right. In our case, we needed a bidirectional communication channel, and we chose WebSockets for that reason. So these are some interesting numbers when we think about the advantages of using WebSocket over HTTP. This is about metadata overhead. So with the WebSocket protocol, with each message sent, there are 2 to 14 bytes of metadata overhead. With server-sent events, 5 bytes. And with HTTP, with each request and response, there are 500 to 800 bytes of metadata, without counting the cookies. So this is a significant difference. So to recap a little, in the past few decades, we've seen an evolution from hypertext documents and web pages to dynamic and interactive web applications. HTTP was not designed for web apps. HTTP was designed with simplicity in mind, and the metadata overhead I just mentioned makes it a less than ideal choice for real-time communication. So to improve the performance of our application and the user experience, we want another model of communication, where the server can pass data to a client without prior client request. This is made possible by WebSockets. WebSockets provide a very interesting alternative, but they do have some downsides. Two major pain points when working with WebSockets are compatibility with existing infrastructure, as WebSocket is a different protocol, distinct from HTTP, and scale and security. Many of the existing components of the infrastructure, for example, servers and load balancers, are built, configured, and maintained with HTTP in mind. The final question I want to address in this section is real-time hard? Well, it depends. Real-time can be simple or hard, and it depends on the requirements of your application. Does it require data persistence? Does it need to scale? How secure should it be? Building a simple chat app is actually very easy to do. There are many libraries out there that make working with WebSockets easier. If you want to add real-time to an existing application, that could be another story. You might need to make a lot of modifications to your existing code base, and it can be worth considering putting that logic in a separate place. Same goes for building a resilient and scalable application. This is a new set of problems that could be difficult to handle if all the logic sits in one place. So, as I mentioned in the beginning, River is a drop-in real-time service. That means it's a separate component. Anytime you add an extra piece to your system, it brings in some additional complexity. And as a general rule of thumb, you should only add complexity when you really need it. So the need for a separate real-time service has to be justified. In this section, I want to look more carefully at the idea of a separate real-time service. We've already talked about the idea of persistent connections and how different it is from the usual request and response cycle. What we haven't mentioned yet is that your server, a process, is now responsible for maintaining the open WebSocket connections. Having a separate server dedicated to maintaining these connections will allow you to offload the management of persistent connections from your main application server. This is a known issue, as illustrated by this quote. So HTTP is optimized for short and bursty transfers. As a result, many of these servers, proxies, and other intermediaries are often configured to aggressively time out idle HTTP connections, which, of course, is exactly what we don't want to see for long-lived WebSocket sessions. So in short, a stateless request and response cycle like HTTP and persistent connections like WebSocket have different technical requirements. These in turn can influence the configuration of your server and cause issues that will be amplified as the load on your server increases. This is the same idea, a bit more forcefully said by the creator of the Flask framework. Keep your WebSockets miles away from the rest of your application code. Keep them in a separate server if you can. They have completely different performance characteristics than your regular HTTP request. So this is basically the idea of separation of concerns. You have two different pieces of functionality. They do something different. Keep them in a separate place. More generally, this idea plays well in a microservices architecture, where each component can scale independently according to its needs. Which brings me to the next point. What if you need to work not only with one server, but with multiple backend services? Again, this is commonly referred to as a microservices architecture. With a microservices architecture, instead of working with one gigantic code base, your application logic is split into multiple smaller services. Now, if you want to add real-time functionality, does it mean that each backend service must manage both HTTP and WebSocket connections? This will look something like this, or probably more like this, since each backend service needs to maintain an open connection with each client. What we really want is something like this: a separate real-time component responsible for managing the WebSocket connections and providing the real-time functionality. The backend services can now send normal HTTP requests to the real-time service. In a sense, they are now decoupled from the clients, as it's the real-time service that is responsible for sending messages to the clients. So, where does that leave us? At a very high level, what are the pieces of a real-time application? Well, real-time applications consist of clients, a real-time communication layer, and backend servers. So before handing it over to Mark, I want to take a moment to go over a few communication patterns and see where that real-time layer fits in. You may have heard the terms publish and subscribe in the context of messaging. This is often referred to as the pub/sub messaging pattern. The exchange of messages can happen between backend services or between the backend and the front end, as in this case. So keep in mind that here we're talking about a browser-facing pub/sub system. The backend services publish events to the real-time service, which sends them to the subscribers. It's a many-to-many relationship. Some obvious advantages of this pattern are that it decouples the publishers from the subscribers. They do not need to be aware of each other. Publishers simply publish events to a specific channel, while subscribers can subscribe to a channel in order to receive events. With this decoupling, it also allows multiple receivers for a single event. And finally, it provides application developers with a simple interface for sending messages in a consistent format. This is basically a variation of the same pattern. So generally, events can be almost anything: a change in a database or a message received from an external API. With this triangular pattern, messages sent by the client to the server over a normal HTTP request and response cycle are treated as events to be published. As you can see, the real-time service is added to an existing application without the need to modify the existing HTTP communication. I won't go into too much detail since Mark will now take over and walk you through a concrete example.
Thank you, Catherine. Let's take a look at what is needed to add real-time functionality to an existing application. We'll use a discussion forum as an example. A traditional discussion forum does not usually have real-time features. And in this case, to know if a new message is in the forum, a user would need to refresh her browser. What are the actual steps needed to add this real-time functionality to an existing discussion forum application, such that a user doesn't have to refresh her browser to see new messages? Let's examine how the request-response cycle changes, if at all, and how events can be sent to alert our users of new messages in real time. Here we have an existing discussion forum application. The application server is on the left and our client is on the right. We're leaving about the database for clarity, but a persistent data layer does exist here. Of course, there are many clients, but we will look at just one at a time here for simplicity and clarity. Just like any other CRUD application, to add a new message to the forum, our client sends an HTTP post request to the server. The server then validates the request, saves it to its database, and sends back a response with a new web page with the client's new post, telling everyone how much she loves dogs. This is as expected, but what happens when a second client makes a post? Here we see a second client making a new post to the discussion forum, but of course our first client can't know about it without refreshing her browser. There's no open channel of communication between the server and our first client. What would it look like if we did have an open channel of communication? To be able to add real-time functionality to our application, we'll open a WebSocket connection between the client and server. We'll use this WebSocket connection to send update to the client when a new message comes in. Now when DogFan55, our second client, sends her message declaring her love for dogs, our server is able to update our first client without any need for her to refresh her browser. This update happens via a WebSocket message sent over our open connection between the server and our first client. So far, we have talked about how to add real-time functionality to our application without adding any external pieces to our infrastructure. And as Catherine talked about before, this can be a valid approach for some use cases. But River is a separate service. How does a separate service actually work with an existing application like our discussion forum here? Now we see River in the picture. Our application still has its existing HTTP communication paths. We want to add real-time functionality as simply as possible, so we're not going to alter these paths at all. But what is the first step that needs to happen here? First, our client needs to open a WebSocket connection with River. It is through this connection that the client will receive updates without having to refresh her browser. Second, our client needs to tell her which messages she wants to receive. River may be sending updates concerning many forums or subforums, and she doesn't want to receive every new forum post, only those new posts for the forum she is currently viewing. She is currently on the dogs forum, so she subscribes to the dogs channel. Our client makes a new forum post in the usual manner via an HTTP post to the server, and the server saves the new forum post to its database. Now our server needs to somehow notify River of this new forum post in the dogs forum so that all clients that are subscribed to the dogs channel can be given the update of the new forum post. To do this, our server publishes to a specific channel, here the dogs channel, via an HTTP post request to River. We can think of this publishing as an event about which all subscribed clients will be notified. Finally, River takes this publishing of an event, turns it into a WebSocket message, and sends it to all the clients that have subscribed to the dogs channel. Here again, we are showing just one client for clarity, but you can imagine many clients all looking at the dogs forum and receiving this message in real time. Now we can see the overall pattern of the browser-facing publish-subscribe model take shape. Our existing application does not modify its HTTP channels of communication. The application publishes events to River, and the clients open a persistent WebSocket connection to subscribe to and receive events from River. Now we can see the bidirectional nature of the communication between River and its clients. The need for bidirectional communication is the reason we chose to use WebSockets over server-sent events. If you recall, server-sent events only permit one-way communication from server to client. Our clients need not only to receive messages, but also to send messages to unsubscribe to and subscribe, or to subscribe to and unsubscribe from channels. Of course, we can have many clients, not just one client, and many backend services. River is unconcerned with which clients are subscribing, and also unconcerned with which backend services are publishing. It simply accepts publish events on a specific channel and broadcasts that event to subscribed clients. But we've introduced one problem now. How does River know who these publishers and subscribers are? How does a separate real-time service authenticate if it is decoupled from the backend services which it supports? We will get to our solution to this problem later in our presentation. Catherine is now going to talk about existing solutions in this problem space.
Thank you, Mark. So before going into how we actually built River, I want to say a word about some of the existing solutions. As we said before, this is a well-known problem. And once you have decided that a separate real-time service would work well for the needs of your application, you have quite a few options. Broadly speaking, the existing solutions can be divided into two categories. On one side, there are many open source libraries to serve a very wide variety of needs. We've looked at quite a few of them, and they were definitely an inspiration to us. Centrifugo, for example, is a scalable real-time messaging server written in Go. It runs as a separate service and maintains persistent WebSocket connections with clients. It follows a very similar pattern to what Mark just described and presents itself as a user-facing pub/sub server. Its use case is very similar to ours. It has been tested at scale and is under active development. On the downside, while it has been used at scale, it's not out of the box ready to scale. The deployment scenario is left to you. And while there are some good instructions on how to deploy and configure your server, that complexity is still yours to manage. On the other side, there are many profitable companies built around this problem space. These are hosted paid services. We've built some demo applications with Pusher, and it's very easy to use. It provides a simple web interface for creating real-time APIs, libraries for multiple languages, and strong guarantees. On the downside, it will cost you some money. The free plan will give you up to 100 concurrent connections. To support 10,000 connections, it will cost you $500 per month. So looking at these options, we thought there was a space in between these two categories. The open source solutions were great, but difficult to deploy. The commercial solutions were easy to use, but costly. So we decided to build a simplified open source version of Pusher. Our main goals were to be easy to deploy and ready to scale. Exactly what the open source solutions don't give you. The trade-off we made was to keep it simple. We don't offer many features beyond the core publish and subscribe functionality. There is another non-open source solution we've looked at and that I want to mention. The Zone is a sports streaming company. We were interested in a specific problem they solved with their own in-house solution. The problem wasn't the streaming itself of live events, but publishing live updates to millions of users eagerly waiting for this critical information. They looked at Amazon Web Services for a good solution and didn't find something that matched their needs out of the box. So they came up with their own solution and wrote a few good articles about it. Their requirements were pretty similar to ours, so this piqued our interest. They needed to publish sports updates to users, allow users to subscribe to new messages, and perform with high traffic on a global scale. In the next slide, I will show you a diagram of the infrastructure for this specific solution, a system they call Puppy. There are many pieces there, so don't get overwhelmed. I just want to point out a few interesting aspects. So this was an inspiration for us while building River, as we knew it had been tested in real life under high load and proven robust. It was also a validation of the use case we had in mind. What I want to point out is simply the overall shape of the system. At the right, users subscribe and receive updates through the application load balancer. To the left, backend services can publish events. The whole centerpiece is the real-time layer, and the WebSocket server lives as a containerized application deployed through the AWS Elastic Container Service. Now, there are many other pieces in there, but it's enough said about existing solutions. Mark will present River and the specific choices we made while building it.
Now let's talk a little bit about how we built and designed River. When designing River, we had a few goals in mind. We wanted it to be easy to use, easy to deploy, and ready to scale. To achieve these goals, we had to make a few trade-offs. First, River has a simple interface and not many features or options. And when River is deployed, there's no configuration. Finally, it deploys on Amazon Web Services only. So far, we have looked at how River interacts with an existing application and have explored this triangular pattern. Now let's zoom in on River and look at the components and resources that make up its internal infrastructure. At its heart, River is a Node.js process running a WebSocket server. That's it. While a single process on a local machine can provide all the functionality and features of River, we had something else in mind. We built River to be resilient and ready to scale. Here we see our same familiar triangular pattern, but turned on its side. We still have our three pieces, the backend services, the clients, and River, but here River is represented as a single Node.js process, which is where we started in our development of River. Notice that our Node.js process is not only accepting and holding WebSocket connections, but it is also accepting the publishing of events from the backend services via HTTP post requests. Since we decided to work with AWS, we needed a place to put our Node.js process. To start with, we put it in an EC2 instance, AWS's standard virtual private server, and this worked. At this point, River has all the functionality that we have discussed so far and can actually be the separate real-time service that we have been describing. But we knew we would want to be able to horizontally scale, so we added another EC2 instance, which brings a couple other pieces that I will introduce. We knew we wanted to be able to have more than one instance of the River server running, one for resiliency, such that if one server goes down, another is available while the first one gets back on its feet. And two, to be ready to scale horizontally to be able to handle more traffic than one EC2 could reasonably handle. But this second instance introduces new problems. How do the nodes communicate with each other? When I say nodes here, I mean an EC2 instance. If an event gets published to one node, how does the other node know about it? To solve this first problem, we added the Elasticache for Redis service, which is Amazon's drop-in replacement for Redis. Redis is usually thought of as a key value cache, something that it does very well, but here we're actually not using it as a cache. Redis also has a very powerful built-in publish-subscribe mechanism, and here the nodes are the actual publishers and subscribers, and Redis allows the nodes to communicate with each other. Just to reiterate the point here, this is an example of an internal or backend service pub/sub, and not the same pattern that River fits into that we have been talking about overall, which is that of a browser-facing pub/sub service. We still have a problem on the other side of our nodes now. We don't want to have two different URLs for accessing River, so we added a load balancer, in this case an application load balancer, which is a subservice of AWS's Elastic Load Balancing service. The load balancer serves to distribute traffic between our nodes and provides a single point of entry for our clients and services. At this point, we felt pretty happy about our system, but we noticed one issue, and that is the fact that our node processes are handling both WebSocket connections and HTTP requests for publishing events. We are mixing WebSockets and HTTP, and as Catherine alluded to earlier, this is not the best idea. Is there a way we can have a separation of concerns? Since Redis is acting as our publish-subscribe mechanism for our nodes, is there some way we can publish to Redis directly? So what we did was add this back channel, as we like to call it, for publishing events via HTTP. Now River has two entry points, one for browser-based WebSocket connections, and one for services to publish events to River via HTTP. The WebSocket connections are now completely decoupled from the HTTP publish requests. The API Gateway service exposes a public URL, and when a publish event comes in via an HTTP post request, the Lambda function validates this request and sends a publish event to Redis. Redis then publishes the event to the node subscribers and then on to our connected clients. Now we have a pretty robust system with a nice separation of concerns, but thinking about two of our goals being easy to use and easy to deploy, we have an issue here. EC2 is a great service and gives developers a lot of power and customization, but also comes with some burdens. Upon deployment, we need to apply security updates. We need to make sure the correct version of Node.js is installed. On an ongoing basis, we need to apply further security updates, operating system updates, manage the logs, and just in general, all of the work that comes with managing servers. We wanted to abstract all of this away for users of River, so we decided to containerize our Node.js process and move to a different AWS service. Now we have the final version of our infrastructure, and as you can see, we have moved from EC2 instances to Amazon's Elastic Container Service. We have taken our WebSocket server and put it in a Docker container, which allows us to focus solely on the business logic of River and not concern ourselves with server maintenance at all. We no longer have to worry about node version conflicts or logs filling up, and can simply deploy our Docker container without thinking about underlying dependencies. Elastic Container Service is a fully managed container orchestration service. ECS has two launch types, the EC2 launch type and the Fargate launch type. We chose to use the Fargate launch type, which Amazon describes as, quote, serverless compute for containers. We also put our internal infrastructure inside a virtual private cloud. This allows us to provision a logically isolated section of the AWS cloud and creates the virtual network over which we have complete control. As I mentioned, ECS has two launch types. With the EC2 launch type, which we did not choose, the developer has to manage the instances on which ECS runs. The developer must provision and scale clusters, patch and update servers, and other tasks associated with server maintenance. In other words, the same problems we were trying to move away from when choosing a containerized approach. With the Fargate launch type, AWS abstracts all of this server infrastructure, abstracts away all of this server infrastructure. We only need to define our tasks and services, which tell ECS how our container should be run, and Fargate takes care of everything else. This allowed us to meet our goal for River of not only being easy to deploy, but easy to use as well. Now, Catherine is going to talk about how we automated the deployment process and the associated challenges we faced.
So, as you can see, while building River, we faced significant challenges. That was only half the battle though, as we didn't want to only build River for ourselves. We wanted to automate the deployment so that other people could easily use it. Now, I want to take a second to come back to this idea of cloud native. We didn't want to throw a lot of buzzwords at you right at the beginning, but now that you've heard Mark describe our infrastructure, we're in a much better position to talk about this idea. Containers, container orchestration, and serverless functions are all part of what being cloud native means. These have big advantages that are worth mentioning. They help us build systems that are resilient and easy to manage. When you combine these with automation, you allow engineers to make high-impact changes easily. Another common element of cloud-native systems is the use of declarative code to describe the infrastructure. And this is what I want to talk about now. This diagram represents different ways to interact with AWS, from manual towards automation. These are alternatives that you can choose depending on your needs. Many people will be familiar with the web-based management console, and it's a good entry point in the world of AWS. It allows you to create your resources easily by clicking through the web interface. It's not an option though when you want to automate the process, as it's not easily repeatable. For that, we have to look at SDKs, software development kits, and blueprints. SDKs allow you to write scripts in a familiar programming language to build your infrastructure. This is great, but anyone who has worked with these scripts can attest that it's still a lot of work. Defining your resources in a specific order and having them interact one with another is not always an easy task. In response to that, a new category of tools has emerged, often called blueprints. The difference between SDKs and blueprints is the difference between how and what, between an imperative language and a declarative language. With an imperative language, you give specific instructions on how to achieve an outcome. With a declarative language, you simply describe what outcome you want. Now, I want to backtrack a little and walk you through a few different scenarios of creating a Lambda function. I chose the Lambda function because it's a relatively simple resource, and I wanted the code to fit on the slides. You can imagine that for a more complex resource, such as an ECS cluster, the overall complexity would be much greater. This is how you create a Lambda function using the command line interface. You need to first define the function itself and manually zip it. Then run a long command from your terminal with many flags. I want to attract your attention to the last line, where the Lambda function is assigned a role. This is a major pain point when deploying AWS resources. You have many different resources and they need to communicate in a secure way. For that, you use roles and permissions. In this specific example, the role was created by another long command that I haven't included on the slide. Of course, the command line interface was not an option for us as it doesn't allow for automation. So we looked next into these blueprints I mentioned, with AWS CloudFormation templates being one example. So these are JSON or YAML templates where you simply describe what resources you want and what they should look like. You will still need to describe roles and permissions, but it makes the deployment consistent and repeatable. This was definitely a step forward for us, but on the downside, these templates are not very user-friendly. They can run over many hundred lines of code, and most of these are simply default settings. So you end up copy-pasting boilerplate templates provided by AWS and looking through those hundreds of lines for the specific parameter you need to change. While researching better options, we came across AWS Cloud Development Kit. It's a very interesting concept as it allows you to write code in a familiar language, such as JavaScript or Python, and model your infrastructure using object-oriented code. Under the hood, it will generate CloudFormation templates for you, these JSON or YAML files, pre-configured with sensible defaults. It makes infrastructure components easy to customize and easy to share, in accordance with the object-oriented code reuse idea. And it makes your whole infrastructure easy to deploy and easy to tear down. On the downside, it's very new as it came out in 2018. And while the docs are good, there are no books yet on the topic and not a lot of good examples. So for more specific configuration requirements, you're on your own. Overall, though, I must say that it worked really well for us. And this is an example of what it looks like. The Lambda function is simply a JavaScript object. So I know there's a lot of code, but basically that's it. And another advantage of how easy it becomes for your resources to interact one with another. As they are defined as JavaScript objects, they can easily communicate within the code itself. The complexity of defining roles and permissions that I mentioned before is abstracted away from you. This line is all that's needed to include the Lambda in a virtual private cloud that allows it to interact with other resources belonging to the same private network. That VPC itself was created as an object in the same file, and it's easy for me to refer to it from within the code itself. So to give you an idea, our main deployment file is about 150 lines of code, and that file generates more than 1,000 lines of CloudFormation templates, these long YAML files. So for us, it was a clear win. Now, we've talked a lot about how we built River and automated its deployment. What I want to emphasize is that our goal was to take that complexity away and provide a tool that's easy to use. So this is what we're going to talk about in this concluding section. Hopefully, it will be a bit lighter on the technical side. Deploying River is one command. After cloning the repository, you just have to type cdk deploy, that's all. The end result is that all your resources will be created on your AWS account. As you can see, the process takes a while, but it's meant to be done once. Know also that it's one command to roll back all these changes. So it makes it easy for you to test if River is a good fit for your needs. As we mentioned in the beginning, River is meant to be used alongside an existing application. So besides deploying it, you also need to interact with it. This is what these outputs are for. We provide libraries with a clean and simple interface to make it easy to interact with River. This is an Example Express app on the server side. So you can simply include the River library as a module. You initialize it with your own API gateway endpoint and a key. Whenever you want to publish a message, you simply need to add one line of code. In this case, every time a post request is received for the add task path, that event will be published. Similarly, on the client side, you can include River as a module. You provide your load balancer endpoint and a valid JSON web token. You can subscribe to any channel you want and instruct River on how it should react to specific events with an event name and a callback. Now, this is a very simple demo, but as the end result of these few lines of code, your existing application is now a real-time application. These are two different browser tabs, and they represent two users that could live in different cities, like Mark in New Mexico and myself in Montreal. When one user updates the state of the application, the UI gets immediately updated for both users without the need to issue an HTTP request. So I will now let Mark say a word about authentication and about our load testing results before closing the presentation.
Thank you, Catherine. Previously, we had mentioned the problem of how does this separate service know who's connecting to it? How can we make sure that only certain clients can establish a connection to River? The previous slides gave a little hint, JSON web tokens. When River is deployed, a 256-bit secret key is generated, which is used to sign the JSON web tokens. These tokens are what allows River to be decoupled from the application server, but also able to authenticate clients. When a client connects to River, a valid token is expected. Let's look at an example of how these tokens might be generated and passed around among the three pieces of our triangular pattern. After River generates the secret, it's shared with the existing application. Before attempting to connect to River, the client requests a token from the application server and sends along its cookies. And since this client is presumably logged in, the server will have some notion of who this client is from its cookies, and will verify that indeed this client should receive a token. The server then generates and returns a valid token signed with the River secret. The client then establishes a connection with River. Note that River allows a connection to be established from any client, but it expects a valid token within the first 15 seconds of connection. Otherwise, the connection is terminated. The client then sends a WebSocket message containing the valid token. River uses the secret to verify the token and sends back a message notifying the client of successful authentication. Finally, River adds this client to its pool of authenticated clients, which allows it to subscribe to channels and receive messages. Note that this is just an example workflow, and River doesn't make any demands on how tokens are issued, passed around, or how their expiration time is set. This is left up to the application developer using River. The only thing that River expects is a valid JSON web token within that first 15 seconds of connection. For the final section of our presentation, let's talk about load testing. If you remember, one of our goals for River was to be ready to scale. To know if we had actually met that goal, we needed to test River under some sort of load and attempt to simulate the real-world conditions of a small to medium web application. To know if River could stand up to such conditions, we set some goal numbers. We wanted to have thousands of stable, concurrent open WebSocket connections, thousands of messages per second being sent by the server, and the ability to handle 100 new connections per second. To synthetically generate clients, we use the Artillery IO testing library, which gives native support to Socket.io, River's underlying WebSocket engine. We set up 2 EC2 instances to run Artillery. We used 2 instead of 1 because if we asked Artillery to generate clients too quickly, it gave us high CPU warnings, which could have led to erroneous test results. So we split the load onto two EC2 instances. 2 containers was just an arbitrary number we picked so we could extrapolate how much load the system can handle for a given number of containers. To have our server generate lots of WebSocket messages, we use the concept of a presence channel. This is a special kind of channel where when a client subscribes to the channel, this subscription event prompts the server to send a message to all the existing subscribers on the channel. Here we see a 4th subscriber on the left, causing the server to send a message to each of the 3 existing subscribers on the right. You can imagine as the number of subscribers grows, the number of messages being sent each second grows very quickly. For example, the 1,000th subscriber to this presence channel will prompt the server to send 999 messages. And if we're generating many clients every second, you can see that there will be a lot of messages flying around once we have many clients connected and subscribed. So in the end, how did River do? To start with, we were able to support 20,000 concurrent connections without any errors. At the beginning of the test, River was able to add 100 new connections per second, but by the time we got to the end of the phase of the test where we were adding clients, this rate decreased to about 15 new connections per second, probably due to the large number of presence channel messages flying around at that point. During the peak of the presence channel messages, we estimate that these were being sent at the rate of 300,000 messages per second. This may sound like a lot of messages, but keep in mind that these are very lightweight text-based messages, around 37 bytes each. And note that these are not HTTP request response cycles, but messages being sent over an existing connection. Despite not reaching the goal of a steady addition of 100 users per second, we felt that we met our overall goal for River to be useful as a real-time service within the context of small to medium web applications. We're still working on River. We have a few ideas for future work. AWS gives us a secure TLS encrypted web endpoint for the API gateway service where backend services publish events, but its application load balancer service, the endpoint where clients connect via WebSockets, does not come with TLS out of the box. To enable secure WebSockets, a developer using River would need to add his custom domain and encryption keys to the application load balancer. This is a straightforward task, but we would like to add an option during deployment to automate this. Right now, we have an API key and secret for authentication, but we could better leverage some Amazon services to provide stronger security for both the API gateway and the secret that validates JSON Web Tokens. We could leverage the Cognito service as an identity provider for JSON Web Token authorization for the API gateway. AWS also has a service called Secrets Manager that would allow a rotating and more robust secret for our WebSocket server. Finally, a feature we would like to add would be this idea of a message cache for dropped connections. Imagine if a user lost her WebSocket connection for a short period of time, like going between cell towers or a train going through a tunnel. Then when she reconnects, she picks up with River right where she left off, not by having to access the applications database, but by accessing River's cache of recent messages. So we've reached the end of our presentation about River. Thank you so much for coming and attending our talk. We have time for some questions now. Here we got one question. So Melissa asked about the cost we had during testing. And the average expense we hit with AWS billing for all that usage. I don't know if there's a particular way for river users to anticipate their costs. We got our AWS bills at the end of last month, um, and it involved a lot of other costs for just like developing and setting up things. So I don't know if Catherine, you have anything to say about that?
I think there will always be a cost because it's a very robust infrastructure. So it cannot be free. We try to lower the cost by being ourselves, like River, free. As Mark said, on the short term, the cost is low. Usage over a long term is something we could not assess. But I like your idea, Melissa, of like maybe being more clear about extrapolating. I think you said, like, if this is what it costs for a week, how much would it cost you for a year? And then being better able to compare with existing solutions.
It also depends on like how you provision how you set everything up. Like right now, River is set up to default kind of choose like the smallest sizes of AWS resources. Like for example, the Redis piece that we picked is, I think it's like 1 cent an hour or something like that. But there's other Redis services that are, you know, a few dollars an hour. So it depends also.
We also have two other questions that are less technical, but I think they're interesting. One is from Derek, and Derek asks, which unique challenges did you face or benefits you experienced working as a team of 2 as opposed to 3? I can start maybe, and Mark, you will jump in. I think it's kind of obvious in the sense that when you're 2, you fight less because we're only 2%, we get along very well, we're both very respectful of each other's ideas. So I think in that sense, for specific parts of the project where you actually need to agree, and it's not a given that we will have the same opinion, so we just have to let the best idea win. I think there is an advantage of being 2, and it depends on the personality of the team member. On the downside, of course, it's more work. So the workload falls on the 2 of us. And when there are lots of tasks that need to be done, it's a lot for sure. Sometimes I think we would have wished to offload some of the work to someone else. But overall, I think it was a very fun experience to both of us.
I'll just add that I think working with Catherine was very easy and smooth and enjoyable. So that wasn't a challenge at all from my perspective.
Yeah, I think we were lucky because we get along and we have complementary strengths, which I think is important. But I think I want to write a whole Capstone article on collaboration because it's a very important topic. And after kind of a few intense months, I have a lot of reflections on the topic. So it might be coming soon. I'm reading Danielle's question that was also mentioned on Slack recently. So he's asking, Catherine, you mentioned that you had a lot of inner resistance to AWS. What were those? How were you convinced otherwise? As well as how laborious is it to hypothetically, okay, that's another question. So 2 questions. First question would be like, where was my inner resistance coming from? The second one is like, how could River work with a different cloud services? Maybe the second one I will leave to Mark. I want to say a few things about the first question without getting too deep in the weeds. I think my inner resistance, I'm not sure it was completely justified. I was definitely the one, it took a long time to convince me to go with AWS. I think that part of it was like my inner teenager was just resisting the idea of going with the mainstream player. And we did spend a lot of time exploring other ideas, right? And I personally spent a few weeks exploring very fringe ideas and reading a lot on different topics until I realized the following. So I was kind of getting too far away from the mental model I know. So these fringe topics were very interesting, but, and I think it was mentioned in Slack also, the Capstone project is a balance, right, between different things. So you have to be able to achieve something in a given time frame. It has to resonate well with your teammates, and it has to resonate well with the job market. So at some point, I understood that my research were going too far away from these goals. And Mark convinced me to try to AWS. And actually, when I started using it, my inner resistance, that was not kind of a valid reason, melted away because it's a very powerful model. And again, as was mentioned on Slack, it's not necessarily AWS related, right? It's cloud services. So again, suddenly my inner resistance transformed into a fascination because it's very powerful. It gives individual developers a lot of power. And I think suddenly we felt like we could build an empire from our own little home office, which is really fun. So I think it's definitely worth exploring. And again, keeping in mind the different goals that you want to achieve with your project. Yeah, so this was a long-winded answer to this question. Mark, do you want to address the second question of hypothetically, how could we connect River to a different cloud service?
Yeah, that's a good question. There are definitely a lot of pieces that could be reused since our WebSocket server lives inside of a Docker container. That, of course, any cloud service that you could use Docker on, you could directly use that, and the libraries that interact with that Docker container. As far as like replicating something like we did with AWS, I'm not exactly sure, mainly because I've never worked with different cloud services besides AWS. But my guess, it was a lot of work for us to set up this and automate the deployment of this particular AWS infrastructure. So my guess, to set up something comparable in a different cloud service, it would be equally time-consuming and challenging. I think there's a couple chat.
There is a question in the chat. Thank you, Ronnie, saying excellent talk. So how did you guys, how did you guys come to a decision on specifically 15 seconds for a connection to be made, and what is the logic behind it in terms of security? Mark, correct me if I'm wrong, but I think there we base ourselves on the existing standards. So maybe, I hope it was clear from the presentation, but we looked at a lot of existing solutions. And we looked at the way they did it, and of course, examine if it made sense. And I believe this is kind of an industry standard, the 15 second.
Yeah, I think it's just like an industry. Yeah, we didn't just like pull it out of a hat, if that's what you're wondering. It's kind of like an industry standard. If you look at different libraries that work with JWTs and WebSockets, it's kind of standard. It gives the client a chance to send that message with the JWT, kind of in the same way that any HTTP endpoint can be accessed by any client in the world. Like, anyone can connect to River, but it'll only last for 15 seconds if you don't have that JWT. Of course, I mean, that could lead to if somebody was like trying to DDoS River, like, and doing 1,000 new connections per second for 15 seconds, that there could definitely be a problem. But it's kind of a trade-off that has to be made at some point.
I see that there are no more questions coming, so I just wanted a few concluding words, right? Thank you all for coming. I want to give a shout out also to the other members of this Capstone cohort. I think they did amazing work. So Team Maestro and Team Jade, I'm very impressed by their project. If there is one thing I've learned in these past few months, it's the power of collaboration. It's very, very powerful. So it was like a pleasure to work with these talented engineers, and especially with Mark, of course. That was a great teammate. So thank you all. Thank you, Sir John, for hosting. If you have any questions, we love to talk about this project. So it's difficult to convey everything in a presentation. So feel very free to reach out to us for questions, generally, or technical questions. So thank you, everyone.
Thank you so much for coming.